So let's say x and y are so let me just do are two discrete unknown variables. Suppose, and let's say x is from the same sample space to range T, y is sample space to range, let's say V. Okay, and let's say E of x is finite. So E of x is finite. So is E of y. So is standard deviation of x, and so is variance. So standard deviation of y. So now, if I look at the random variable z equal to x plus 1. So the first thing we observe is that we know already that expectation is linear, right? So linear means E of z is just going to be E of x plus E of y. Right? So that we have shown before, that the mean is linear. Right? So shown before. Shown earlier, E of z is just E of x plus E of y. Variance. Now, what is variance of z? This variance. Variance of z, we know is that is going to be, now this is finite because E of x is finite, E of y is finite, sum of two finite people are finite. So variance of z is what? Is z minus E of z the whole square. So E of z the whole square. That's what variance of z is. Or we could use the previous result, which is this 4.2.5. That's the same thing as, this is from theorem 5. That's the same as E of z squared minus E of z the whole square. That's the same thing. What is z squared? Z squared is x plus y the whole square. So now, which is what now? Which is just x squared plus y squared plus 2 times xy. That's easy to see, right? So if again now use linear expectations, so that's E of z squared is the same as, so using linearity again, of expectation, E of z squared is the same as E of x squared plus E of y squared plus 2 times exy. Of course, E of xy could be infinite or finite, I do not know yet, but that's what it is. That's what it is. That's it. So now everything is sort of adding up in some form. And then E of z the whole square, so that's just algebra. So that is algebra. So E of z the whole square is going to be E of x plus E of y the whole square, which is just E of x squared. So E of x the whole square. Sorry. Just E of x the whole square plus E of y the whole square plus 2 times E of x times E of y. Very good. That's just everything is finite, so I can sort of do this whole calculation. Because I assume that E of x is finite, E of y is finite, and SD is finite. So therefore, okay, the only thing I do not know is E of xy, how it behaves, but modulo that, all other numbers I'm adding are finite. So therefore, E of Z, so therefore variance of Z, therefore variance of Z, which is just E of Z squared minus E of Z the whole square, right, is equal to what now? Is equal to, I'll add these guys, E of X squared plus E of Y squared. Okay. So okay, this I do not know if it's finite or infinite. I'll write this in green, just leave it there. So this could blow this number away, but anyway, broadly, that's what it is. It may or may not exist also, we don't know. But as of now, that's where that is. So assuming E of Z squared exists, yeah. So E of Z squared will exist. It will be either infinity or a finite number because it's a non-negative random variable, and non-negative C is always diverges infinity or it converges. So this number also exists because these numbers also exist. These two also exist. This also exists. Anyway. But we don't know if it's finite or infinity, or minus infinity. And this one, E of Z squared, is minus, what is E of Z squared? Minus E of Z squared, that's just minus E of X squared, E of X the whole squared, right, in a special way, minus E of X the whole squared, minus E of Y the whole squared. And then here I'll write it as minus 2 times EX times EY. So now if I stay a little bit, if I look at these people, what do I get? I get variance of X. If I look at these people, I get variance of Y. And this I'll leave it as it is. I'll leave it as green. So what I get is variance of Z is the same as, so variance of, on this side I have, let me write down in black, variance of X plus Y is variance of X plus variance of Y. And this I will call it a different number. I'll just write it in green, minus 2 times. I'll call this as, it's called the covariance of X comma Y, okay, where the covariance is defined as EXY minus EX times EY. So that kind of determines how dependent the random variables are. Because if they're independent, we have seen E of XY is E of X times E of Y, that's 0. This is something that's kind of an interesting idea to understand. It's an identity that you should keep in mind. So let me mark it in some box, let's say a brown box. Let's say. It's a nice box. So if everything is finite and nice, then variance of X plus Y is variance of X plus variance of Y minus twice the covariance of X plus Y. It's one interesting fact one can use. And one corollary is the following. Let's write the corollary down. This theorem, let's say, which is quite useful. The following, that suppose X and Y are let's say, independent random variables. Then let's try and guess what's variance of X plus Y. Let's suppose let's give all these caveats. Let's say assume mean of X is finite, mean of Y is finite, standard deviation of X is finite, and standard deviation of this is finite. Everything is finite. All these are finite numbers. Then the above everything is okay. So then variance of X plus Y is going to be equal to variance of X plus variance of Y. But look at covariance. Covariance is EXY minus EX times EY. But if X and Y are independent, we have already shown that EXY splits up as a product. So that's it. That's what is a crucial idea. the variance sums up. So independent random variables, the variance will sum up. That's a very, very important observation. Let's try and prove it. Prove is just trivial, but let's try and prove it. So you take, we know from, let's call this as dagger or stop or plus. So from plus, we know variance of x plus y is equal to variance of x plus variance of y plus twice or minus, or no, why is it minus? It should be plus, right? So it's just a plus. Sorry. I made a mistake here, I'm sorry. Just a plus. I'm just writing exactly that, right? So it's just a plus. Plus 2 covariance of x comma y. So therefore, but we know from before, we have seen, I think that was, if I remember correctly, that was theorem 4.2. Where we do this E of x y is 4.1.10. So it's theorem, write down. So theorem 4.1.10 that is if x and y independent, then E of x y is just we showed this that E of x times E of y got split as a product. Right, covariance x y can be negative. Why not? Yeah. So I don't know if in 12th class have you seen this idea of correlation coefficient, which is covariance divided by the product of the standard deviations. That could be negative or positive, right? Between -1 and 1, right? So it's something we have seen before. So therefore, this will imply that covariance of xy is 0. So therefore, variance of x plus y is equal to variance of x plus variance of y, assuming they're independent. Right? So x and y independent means the variance adds up. Very cool. Okay, so I'll conclude today's class with a bunch of examples. Let's try and see a node distribution. Let's try and see how to do that. Maybe I'll just leave this theorem for a little bit and check a little bit. So let me do an example. Example 4.2.8. Suppose x is, let's say, Bernoulli P. That means x takes 0 with probability P and probability 1 minus P, and y takes x takes value 1 with probability P. That's the random variable x. So we know that E of x is going to be equal to just P. This we have seen before. Right? E of x is P, we have seen before. Now what's variance of x? The variance of x is going to be equal to what now? It's going to be equal to E of x minus P the whole square, right? That's what the variance of x is. And what's that going to be? X takes value 0 minus p the whole squared with probability 1 minus p plus 1 minus p the whole squared times probability p. That's how you do it, right? You just do the, because you think of the function. How do you do this? You think of the function as this computation. You think of the function as f of x is equal to x minus p the whole squared, and then you know that e of x minus p the whole squared is just summation over t in t, f of t times probability x equal to t. And that's what I used here, right? Very nice. So what's that going to be? That's going to be equal to, so therefore variance of x is just p squared times 1 minus p plus 1 minus p the whole squared times p, right? That's what I will get, and that's going to be just you can just work the algebra out. It's p squared minus p cubed. Something's wrong somewhere. Oh, that's correct. It's plus 1 plus p squared minus 2p times p, and that's the p cube cancels off, and I'm left with p squared plus p minus 2p squared, and that's just p times 1 minus p. So variance of x is like p times 1 minus p. So here was p was between 0 less than equal to p less than equal to 1. So I don't know if you like think a little bit like this. If you look at the variance of x as a function of p, 1 is here, 0 is here, and let's say this is p, and you think of variance of x as a function of p, that is p times 1 minus p. We'll mark this in green. That's the y-axis. That means, how does the graph look like? It starts at 0, and then comes back at starts at 0 and then comes back at 0, at 1 at 0 again. That's how the variance graph looks like as a function of p, and it's kind of maximum at p equal to half, right? So that's where it's plotted. So that's how the variance of a Bernoulli shifts with p. So at the boundary, the random variable is constant. That's why the variance is 0. And in between, the variance is kind of stabilizing at around a quarter. So let me do another example. Let's do binomial, which is what we like to do. So example, if we take n independent Bernoulli trials, so staple example. So let's say x was binomial n comma p. Of course, I could now I could think of I already know that e of x is n times p, and because we did that before, and I could go and say, okay, fine, variance of x. I could try and go and compute e of x minus np, the whole squared, which is going to be the sum from k equal to 0 to n, k minus np the whole squared times probability x equal to k is n choose k, p power k, 1 minus p to the power n minus k, and so on and so forth. I could try and finish the computation, but since I'm not really good at Olympiad type jugglery like this, so let me try and do a different method. So there's one way you can compute it, but I would like to do it probabilistically. So probabilistically, I view it the following. So I know x is the same as the sum from I equal to 1 to n of xi I, where xi I are all IID, the same distribution, independent and identically distributed. That is IID in short, as the random variable xi, which takes the value 0 with probability 1 minus p, and 1 with probability p. Right? So xi is all Bernoulli p. Right? Xi is Bernoulli. And they're all independent. So therefore, by what this theorem, the theorem number is what? Theorem number is 4.2.6. Right? So therefore, theorem 4.2.6 will imply that variance of x is the sum of I. They're all independent, so sum of I equal to n, variance of xi. But the above calculation, we know that this is the same as summation I equal to 1 to n. Each of them is p times 1 minus p. They're all constant, so the variance is n times p times 1 minus p. Of course, you could have got it from the previous formula as well, but I'd like to do it this way. So it's sort of a nice idea. That is the variance sums up, and it's n times p times 1 minus p. So once you understand this, if n gets larger and larger, your variance is getting larger and larger. It's not going to, and if p is, let's say, between 0 and 1, a fixed quantity, your variance is getting larger and larger. So one can get enough information from a binomial one how to utilize this variance. For large n, how does one understand where the random variable x lies in? Because it's a large variance, right? So it's n time. So this we will see next time. So maybe not this week, but maybe this week. I'm not so sure, but we'll see and see. So how to from an applications point of view, that is, if you were to sample from a population, where some members have a certain characteristic, others do not, right? So this is and others do not. So this is something that's very useful and what's the goal? You do the sampling, and then the goal is to provide an estimate for the people with the characteristic. So the number of people with the characteristic. So this we'll try and explore next time. So we'll try and explore in the next class or next week. We'll explore so. Then the variance comes into play. Other standard distributions, I think I'll let you play with and get it. I'll give exercises, you can try it. Then finish off the other part. Now, I just want to conclude with one small generalization, and I'll stop for the day. Broadly, the above concepts are not restricted to just discrete random variables. You can do the same thing for continuous random variables. There's really no differences. So let me just make a remark and I will stop it. So here are some remarks. So let x be a continuous random variable with PDF f sub x from R to infinity. Then we already know that e of x is given by integral minus infinity x f sub x x dx is when it's defined. You already know this. So same way, similarly, one can define the variance of x as well with the same assumptions. Similarly, under assumptions that e of x is finite, that is, the integral converges absolutely, one can do the same thing. One can define the variance of x as the same as e of x minus e of x the whole squared, and that's just you can think of it as x minus e of x, that's a constant, the whole squared, f sub x at x dx. And the standard deviation, again, this is a squared of a quantity, the integral is non-negative always, and the standard deviation is well defined, that's just the square root of the variance of x. There's really no problem. And equivalent properties of theorems hold, that is, other properties also carry on. So this is one thing. Other properties also follow. Just by instead of using sums, you do integration. That is, a variance a is positive. Variance of a times x is just a squared variance of x. This is an important property that we'll use again and again. Then if you shift random variable, then the random variable variance doesn't change because the spread doesn't change. The same idea of spread works, and then the other thing is that e of xy is again, if x and y are independent, then e of x, variance of x plus y is same as variance of x plus variance of y.